previously you have learned about the kinematics. Kinematic is basically the geometry of motion. And today we're going to study how to apply Newton's second law to rigid body. So there are two kinds of motions that you need to pay attention to. This is pure rotations. And indeed, translation is part of that, but it's relatively simple. And then next, then the combination of translations and rotation, then you're going to have the general motion of that. Okay. So let's see one of the easiest examples that you can visualize. What means the general motion of rigid body? If you now have the two-wheel vehicle, okay, so you can see that two-wheel vehicle can go forward for translations. You can also go rotation about the center. You can also go around a corner with curvy linear motion or general motion. Okay, let's have a few. So what you can see is the two-wheel stabilized vehicle. Okay. Okay. Look like a scooter. Okay. So you can see that with the two wheel you can go around harm and then you can go turning around. Okay. You can see that you can go around. So today, then we're going to ask you, if now you have a two-wheel vehicle, okay, going around a center, okay, for pure rotation, how do you write the equations? 所以你们学的牛顿定律 ，OK， 你之前所学的都是一个单体的牛顿定律。So let's say you have a particle mass is subjected to force. You describe this with motion x. So you are writing the motion x will have velocity, acceleration in the same direction. And then you can now write F equal to ma. Okay? So now our question here is, if you now have something like this, okay? Okay. This might look like a dumbbell, okay? And if now is subjected to a moment to rotate, okay? What kind of motion will you be able to describe it? Okay? So you might have M1, M2, M1, M2. To describe this, you have the angle theta, as well as theta dot angular speed, theta double dot, that is the angular acceleration. So, what should you write? Okay, if you now have moment applied to that, then there must be moment induced J naught theta double dot. Okay, so how this apply? Okay, it might appear a quick jump for you to write this equation, because what you learned before is single mass rotation. You might also learn about a swinging mass that rotates 360 degrees. Okay? So if you are describing this, okay, you might have learned this before. M naught could be F, this is the radius, R, okay, is equal to, okay, because you can write them as tangential forms. Then you have the N, R, double dot. And if you now multiply R on both sides, you have these as the moment, and you have the mR squared as the J naught. Okay? But why this can't be applied directly to a double mass? Okay? I mean, the way of analysis. Okay, the way of analysis here is starting from Newton's law in tangential motion. Okay, why can't I apply this directly? Because you have the rod defining the motion, no problem. This is R1 theta double dot, or this is R2 theta double dot. But the force here could be different. The force here could be F(E1), okay, because it is an internal force. I'm going to write this is lowercase f(E1), then this is lowercase f(E2). Okay, so for the analysis you can't do directly. Okay, you need to do divide and conquer. 我们来看一下，所以这个例子其实很像一个情况哦，我给大家播一下。这个情况有点像这个这个上下单板。So it look like this. I said now I don't care, I don't account for the weight. I just apply the moment. This is the one subjected to vertical gravity. So they are oscillating. Okay? So this one, I'm just applying a pure moment. I just want to account for the angular rotation under the constant moment. So with this, then I come to the analysis. 我们来看一下这个分析要怎么做。这分析其实相对直观。OK， 那我们来看一下。So in this analysis, I'm going to draw two things. One is the top mass, and one is the bottom mass, and two. They are connected by a link. Okay, this is a rod which is massless. Okay, so this is the bob one. Okay, bob number one. This is the bob number two. Okay, it is going through rotations about a pivot. So let's say the pivot to bob 1 distance is R1. The pivot to bob 2 distance is R2. Okay? If you undergo rotation theta, the top bob will go through the displacement of R theta dot 1. R1 theta dot. This one will go through a displacement of R2 theta dot. So likewise, you can get the velocity and accelerations by multiplying the radius with the angular speed and so on. Okay. So next, how does the rotation going on? The rotation is going on when you apply a moment about the center. Okay. So now the thing I would like to analyze is what are the force acting on the bob. Okay? If I'm cutting them, if I separate them, okay? You see, if I now do the separation, the moment is applied Let me change the color to be consistent. The moment is applied at the master's rod. Okay? After making a cut of the rod from the bob, what would you think? If the bob is going forward, there must be a forward force. Let's say it's the internal force F1T. Okay? And if this rotation is accompanied by angular speed, then the bob on the top must be pulled down by F1N, a normal force. Okay? So opposing this internal force is the one acting on the rod, which is F1N, and which is F1T on the top end of the rod. Okay, and then next, likewise, if you are now making a cut of the rod to the bottom mast, M2, okay, this must, M2 must be subjected to a tangential force so that it will move to the left. Since there is a rotation going on, they must be pulled up by a normal force. OK， 同学这个分而治之看得懂吗？所以你一个如果一个扫把 ，OK， 我们只是看单边。你如果去转 ，OK， 如果扫把头是松的 ，OK， 会怎样？你转下去，不小心去抛中。那扫把头会跟着我手臂上下，是什么关系？那切线一定要有力，不然你的力传不过去。OK。So with this, now we're now going to analyze, okay, the rotations. Okay. And then, what is the equation of motion? Okay, for the system. Supposedly, I'm going to find the system, but now I'm going to write the equation by parts. Okay. The first part is what? The first part is M1. Okay. Let's say the bob. Okay. Number 1. How do you write the equation? This mass is going forward by R theta, R1 theta, double dot. And when it's subjected to these forces, okay, you now can write the equation of motion. F1T is equal to M1 R1 theta double dot. Okay, this is a tangential force. And then next, F1N is going to equal to M1 R1 theta dot square. Okay, and then next we see the bottom one, the bob number 2. Okay, the direction here is something like that. Okay, if you write that, you can also write this. The direction here, tangential force, F2T is equal to N2 R2 theta double dot. And then this one is F2N is your M2 R2 theta dot square. Okay, now come to the important part. How about the rod? Okay. How do you write the equation? Okay. Because the important thing is I want to know the rotation. Okay. What can I write? I can write moment summation about the center. Okay. But in this case, you don't just sum up the external moment. You also have to sum up the internal moment due to this internal force at the cutting end. Okay? So in this case, this is going to be the sum that give you the equation. So the bottom one is okay. Yeah, please draw this up. Okay. In this case, what would it be the zero sum? There will be moment coming from, okay, depending how you want to write. If you want to write clockwise following M naught, then you have M naught clockwise, and then next, this top force F1T is rotating about the pivot point O. Then you have minus F1T times R1. And then how about the bottom force? The bottom force, oh, just now I forget to draw, it should be opposite. F to T is F to N. Okay, in this case, then you have also counterclockwise F to T R2. Okay? Take your equation 1A, 1B, 2A, 2B, and now equation 3. If you now do the substitution in, okay, let me write that. This is M naught is equal to F1T R1 plus F2T R2. If you now do the substitution of the expression here, then you have M1 R1 square theta double dot plus M2 R2 square theta double dot. So in the end, you have this expression. 好，同学看到没有？所以这就是从单个字典单版到双个字典 ，OK？ 然后这是双个字典，所以你的分析靠什么 ？OK？ 那你后面的分析 ，OK？ 你可以把它当成一个整体，然后直接套用这个公式。So we now do the divide and conquer to find out what is the equation acting on individual. Okay? But now if you want to find the system equation, how do you write? 所以你如果扫把，有一个扫把头，然后如果说两端都有质量，那你后面写的公式你要怎么写？你的公式要写的话是根据你的扫把的杆虚数的转动乘上你的转动轴 ，OK， 然后质量 ，OK， 所以你的后面写的是什么？作用在杆上的扭力会造成扫把杆上两端质量的加速度 ，OK。那我如果说不要个别分析个别质量的运动，我可以把这两个质量合在一起，它的叫转动惯力乘上加速度 ，OK。So it don't just apply to a simple pendulum. Okay, previously you learned about this simple pendulum. Okay, if you have M here, you have the rotation here. If you are writing a force on here, then you can write moment sum about the pivot is equal to J naught theta double dot. Okay, in this case, okay, what do you have? You have the moment which is the tangent one times the moment arm, which is the L. And then what is the J naught? J naught here is the distance between axis of rotation and the mass point. This is the ml squared theta w. Okay. Yeah, simple. And then next, how to apply this to a compound pendulum consisting of two mass? If you now have this M1 and then M2, and if you are subjected to the weight, okay, this is M2G, this is M1G, and then this one, if you are describing using this count theta, how do you write the equation? Every time when you write the moment sum about the pivot is equal to J naught theta double dot. What is now the M naught? Look at here. The force must break down into tangential part, which is called M2G sine theta, and normal part. Okay? Normal part I don't care so much because normal part will not contribute to the rotation. So the tangential part is this one. Okay, how about the top one? Likewise, this one you have theta here, you have theta there. Your tangential part is M1G sine theta. Then your normal part is M1G cosine theta. Okay? Now look at what caused the moment. You have the moment caused by this bottom weight component. You have these. Okay, now let's see this. This is what you call counterclockwise rotation. Okay, depending how you see, yes, this is counterclockwise. Then you can write this is N1 G sine theta times the radius R1. But now, this bottom part is causing you a clockwise moment. Then you have the M2G sine theta R2. Okay, then they sum up to be equal to M1 R1 squared plus M2 R2 squared times theta double dot. OK， 同学看到没有？我们现在大概是教你怎么去分析，一定要画图。OK， so in your later lecture notes, okay, you might also learn how to analyze the rotation of the T-shaped pendulum. So let me have a quick analysis of that so that you can have a better sense. Okay? Okay, how do you analyze a rod rotation in this case? Let me show you the video. Okay, we previously had this pendulum shown before. In the simple pendulum, the box is much heavier than the rod, so you can negate the weight of the rod. Okay, but now if the weight is removed, you can't negate the weight of the rod itself. The rod itself is a pendulum. Okay. So then, how do you analyze this pendulum motion? Okay. So to analyze this, let's look at one part. This is a small mass, dm, located at radius r. How much is this small mass? If the full length is L with the total mass, this small mass must be the small length, dr, divided by the full length times the total mass. Okay? Then next, how much the distance travel of this small mass? It travel with s equal to r theta. Okay? It travel with the speed of r theta dot. Okay? You get it? So if you now want to find out the moment of inertia, how do you find the moment of inertia? Do you remember that I'm doing the sum of all the small mass radius squared? Okay? In this case, this is small mass. So this sum is integral of radius squared dm. You accept that? And then, so my distance will start from r equal to 0 to r equal to L. Okay? So let's do the expansion. This is your r squared. This is your m over L dr. So in this case, you can get the expressions m over L, and this is your r cubed divided by 3. And then by substituting r equal to 0 to r equal to L. So in the end, your J naught is equal to m over L, and then L cubed divided by 3. So in the end, your moment of inertia is nL squared divided by 3. Okay? So do you get this? Okay. So after you get this, then we want to go one step further. How can you go one step further? Okay. You may only know the rod moment inertia. Okay, how do you write the angular acceleration here? If you are going to write the angular acceleration here, okay, remember what we're going to write? Moment sum is equal to your J naught theta double dot, where O is the pivot of rotation. Okay? Now you have to ask, what is the weight acting on the rod? Okay, later we're going to prove you the point. The force of the whole rod is M1G. It's acting at the gravity center. Okay? So you can now reduce this into two parts. Okay? The tangential part is mg sine theta. The normal part is mg cosine theta. Okay? So now, what is the moment? If you define theta is counterclockwise, look at the force here. The force here is giving you clockwise moment. So this one is minus mg sine theta. This is the moment arm, which is half the length. Is now J naught theta double dot, which is my mL squared divided by 3 theta dot. Okay? Yeah, this is how we write the equation. And then next, how do you do the progressions to more complicated things? I think if you look at your lecture notes, okay, we can go one step further. Okay, you go to read your textbook. What happens if you now have the inverted T-shaped rod? What happens if it rotated? again, we can do divide and conquer. If you now want to write the equation, you still write a pure rotation is due to the moment. It's causing you moment inertia times angular acceleration. Look at here. On the vertical part, it rotates by angle theta. What happened to the bottom part? It also rotates by angle theta. But now, what you can do is, you can do the breaking up. How do you break up the thing? You can break up the thing by vertical parts and horizontal part. Okay? I believe there is internal force, but that's fine because for the moment, if I do the breakup, what it look like? This part, once break up, you might have the counter moment. Okay? Anyway, moment sum, you can write equal to moment 1. This is moment 1 due to the weight 1. Moment 2 due to the rod 2. You have in between M1 2 minus M2 1. They are opposing in direction. So in the end, you can write what is moment 1. Moment 1 is due to the vertical rod. We write it before. This is minus mg minus m1g. Okay, L over 2 sine theta. How about moment 2? Moment 2 is due to this part. Okay, M2G. Look at here. M2G also have a tangential component, but this is M2G sine theta. Okay, again, this moment is, in this case, is clockwise, is opposing to our coordinate. Okay, so you right now is M2G, but because of the distance here from the pivot is L, then you write L sine theta. That sum up to be equal to your M1. No, it's not more M1. Okay, it's not M1 R1 squared anymore, because you got to get the component. First one is what? First one is M1 L squared divided by 3, because this is the vertical rod. Okay, but then the horizontal part. How do you analyzing the horizontal part? Remember, if you have the pivot supporting a horizontal rod, if you are going through rotation theta, almost every part is going by angle theta. So this horizontal part has a moment of inertia of ml squared. Theta 的 OK， 所以同学这看得懂了。所以我们花了比较多的时间专门跟你讲转动 ，OK， 然后你有了这个基础，那你后面就比较好应用。好 ，After that, then we come to the general motion. So this explains why you have this kind of the oscillatory motion. Then next, we come to general motion. In this case, we're going to choose to use a bola. We're going to use a 2 tennis ball bola to show you the general motion. Okay? So beside rotation of the balls, they're going to have translation. Let's see. You see that? translation, but this is 3 ball or 2 ball. Yeah. Shoelace going through a tennis ball, and then now you connect up the 3 shoelaces together. Okay, and then you spin the 3. Okay, in order to make sure the ball is spread. Shoelace at different radius. Okay. So now, rather than analyzing the 3 ball bolas, we come to the questions. In this case, if now I have the 2 balls bolas, if I'm going to have a throw, spin and throw, if I'm going to have a throw, so what will be the motion? Would it be a translation and would it be a rotation? 那我们拿最简单的例子。我们来丢扫把 ，OK？ 那请问它会平移还是会转动？我们来丢看。你看，它是平移还是转动？那我们再丢一次，它抓的地方不一样。我现在抓下面，所以这个是什么？比较接近平移吧 ，OK？ 所以你看到没有？ 你抓的地方不一样，你的运动就不一样。你看扫把头，我抓住这个扫把，我丢，啊，这个主要是什么？主要是转动。So look at here. So when you have the distributed mass, where you hold and where you apply force is causing different kind of motion. So in this case, if I'm holding at the top and pushing it, so you can see that it's mainly rotation. Okay? If I'm holding at the bottom, okay, if I have a throw, okay, largely translation. Okay? Very little rotation. And then now if I hold at the center, okay, then you're going to have a combination of rotation and translation, depending on how far and away you are away from the gravity center. So the trick here is, if I hold at the gravity center, and if I make it a push, then the motion will be largely translation. Okay? Let's prove the point. Why when you hold at the gravity center and give it a pushing force, why will there be a translation? So let's see. Okay? So what our analysis is still remain the same as we did. So I'm going to do some simplifications of our previous analysis. Okay? 那我们就快速去分析一下潜力。So what is different from our previous analysis from the current one? In the previous analysis, you have M1, M2, okay, about the same. But now you have the pivot point O. Okay? Then you apply the moment MO. This will cause you the rotation. But in this case, I'm going to free up the rod. The rod, there is no pivot. Okay? But now I'm going to apply the force F. This is my force point. It is away from M1 by distance R1. It's away from M2 by distance R2. Okay? So in this case, how do you write the equation? Okay? So now, the first thing I'm going to write is, because of being freeing up, okay, I can now write this. M1, M2, if I free up, if you now have the translation, okay, now the thing is going to move together by X. And then the rod could have rotation. So this is now moving by X plus R1 theta. And then how about the mass M2? It's going to move up by X and go back by R2 theta. So what is the total motion? The total motion is x1 is equal to x plus R1 theta. And then how about the x2? x2 is the total x2 is equal to x minus R2 theta. And then where is the force point moving? The force point moving here. Okay. So if I take the quads of the previous analysis, the force acting on the top, you got the F1T, this reaction is F1T also, and then the force acting at the bottom, you have the this is F2T, this one is F1T, F2T. Okay, you see it? Now we're going to write a quick one to give you the idea about translation. Okay, remember how to write the equation? If I now focus on the translation. Okay, Bob 1, you have the F1T is equal to M1 x1 double dot. It is equal to M1 x double dot plus R1 theta double dot. Okay, that's right. And then next, how about the Bob 2? The bottom one. The bottom one is going left. And it's F2T is equal to M1. Okay, be careful. Because this time round I have a coordinate X always to the right. I can't write it this way now. I have to be consistent. If I'm going to follow my coordinate x2 double dot, it is going to be right positive. So this one, no choice, it is negative. Okay? And then the right hand side is m2 x double dot minus r2 theta double dot. You get this? Okay? Yeah. So now, how about the middle rod? Okay, now come to the middle rod. If I'm going to write force sum for the middle rod, okay? This is where I apply my force. This is where my reaction force. Okay? Okay, supposedly the rod should have force sum equal to mass time acceleration times something. Okay? But interestingly, your mass is 0. So the right answer is 0 because this is massless. Okay? So now, what is the force sum? The force sum is then external applied force minus F1T plus F2T equal to 0. Okay? Now if you now do the rewriting, you can write F equal to external force equal to the internal force F1T minus F2T. Okay, recall what is F1T and F2T. If you now write this, you're going to have M1 x double dot plus R1 theta double dot plus this is minus F2T is equal to M2 x double dot minus R2 theta double dot. Okay, you can now do the simplifications because now you have two coordinates. One is the translations, one is the rotation. If you now factor out the one that has to do with the translation, you have the sum of the mass x double dot and then plus M1 R1 minus M2 R2 theta double dot. And then this is your equation. 好，当然我们丢扫把的时候，你大概就应该知道，这个力会造成什么？这个力刚才已经讲过，你丢扫把，平移跟转动 ，OK。那这样的情况底下会有纯平移。So in what situation you're going to have pure rotation? As pure translation. If the second term is 0. What does it mean? If you now apply the force at this point, if this is the force point, did it happen there? If it happened that the force point is 0,这个公式告诉你什么？ If you take the coordinate, this is the y. Okay, this is y1 equal to positive r1. How about this position? This is y2 equal to minus r2. What is your gravity center? Your gravity center is m1 y1 plus m2 y2 divided by m1 plus m2. If you go to do the substitution here, your numerator is 0. And then your gravity center, where is it? The gravity center is the point where you apply the force. In this way, we come to the conclusion that if you apply a force on the gravity center, then very likely you're going to have pure translation. Okay? Yeah. 好。所以我们就跟大家讲了，你看到没有？所以你在分析力的时候，这个钢体的运动，你就可以大概找到它的这个平移的情况。Okay? So this comes to the point. You see here? You now can reduce the equations. F equal to mx double dot plus something times angular rotation. You reduce it to force is equal to force sum times translation at the gravity center. Okay? So in this case, previously I defined my coordinate using force point. Okay? But my question is, what happens if I don't use if the force point is not the same as my gravity center? If the force point is away from my gravity center, what will happen? If you do the same analysis, but just offsetting the coordinate, the top coordinate, top displacement from the gravity center now is gravity center translation plus the distance between the force point and the gravity center plus the distance between the force point and the bob 1. So this is the extra rotation R1 theta dot. And then how about the bottom bob? The bottom bob is now closer to the gravity center, further away from the force point. The distance between the gravity center to the bob 2 is now force point distance minus the distance between the force point and the gravity center. So this is the R2 minus h. Now you can write this as gravity translation minus R2 minus h theta double dot. Okay? With this, if you do the same substitution, you are still going to get mass sum times gravity center acceleration plus something times angular acceleration. This something can be reduced to the height between the force point and the gravity center. 所以刚才讲的就是说，我刚才施力点如果刚好是在你的这个重心，那你会造成转动 ，OK？ 但是你如果刚好你这个 hedge point 呢，上调到上面去，你就不会有转动 ，OK？ 所以它这个是一体多面 ，OK？ 然后我们现在又回到最后，可能我要总结一下，就是说又回到那个 moment equation。刚才讲的是纯平移，那现在如果力点不在重心，你的纯转动是什么？你会有这样的转动。平移已经发生了，不管你怎样，你的力不施加在重心，还是平移。OK， 那这样的情况底下，如果力不施加在重心，那就有转动扭力。那转动扭力自然会造成你的脚架速度。那你脚架速度怎么算？ So how to determine the moment inertia? Okay, because of the time limitations, I'll straight away go to the working. Okay, when you do the moment sum about the gravity center, look at this white black color dot. Okay, the moment here is N times h. This is what you call external moment. But not to forget, if you now free up the rod is subjected to tangential force coming from bob 1 and tangential force coming from bob 2. So there are some typo that I do the correction. Okay. So with this, then you have minus top tangential force times the moment arm, which is R1 plus h, and then minus tangential force at the bottom bob times the shorter moment arm, which is R2 minus h. If you now do the substitution of the tangential force as we did before, then you come to the expression here, the red color thing, right? And then it reduces to this expression. Okay? Now, what is your new moment inertia? Your moment inertia is measured from gravity center to bob 1, which is R1, h plus R1. The moment inertia is R1 plus h squared times m1. How about the bottom bob? The bottom bob has a shorter moment arm, which is R2 minus h. Then the moment inertia is m2 times R2 minus h squared. In the end, you still reduce them to external moment is equal to moment inertia times angular acceleration. With this, then you should be able to solve your latest homework, okay, which is the last part of the homework. And then, yeah, that's it for today. Thank you for your attention. Okay. So the extra examples, you can work it out, okay? And then also the latest slide will give you different references of coordinate. Okay, if you are rotating about a point which is away from the rod, it still works. But your right hand side got to change. Okay, the last part I highlight to you is if you now go and write moment inertia about some way far away, okay, then you are going to write this equation. Let me see. Yeah. If you are writing at the instantaneous center, okay, then you're going to write all this. Okay, so this is the one. If you are right about a point far away, the momentum far away consists of two parts. It's not just your moment inertia, but the gravity center acceleration times moment arm. OK， 好，这个就总结我们今天上的事情。OK， this is what I done for today.